Greetings. So in this presentation we're going to talk about arrays, allocated pointers, and linked lists. A lot of it's going to depend on what we've talked about as far as arrays in the past. So let's start off and do this. Let's say data 100, and that's all well and good. But now let's get it. Let's have it more interesting. So it's a pretty big data array of integers, and what we had said in class was that was worked great, and it wasn't going to override anything, and it's probably going to be pretty safe. But it lacks that data encapsulation or the privacy that we talked about. Now, if we put it here and we make it local to the main function, basically we're allocating that memory off of the stack. And when you're allocating this much memory, let's say it's 10 megabytes or 10 megabytes, it's going to eventually blow up the stack. So these two alternatives are fine and all, but especially for like small data, they're fine. But for large data that we want to keep private and encapsulated, there's a better way to do this. So let's go ahead and include malloc. And what we're going to do, instead of declaring int data like that, which will blow up the stack, however, this is private and encapsulated, what we're going to do is we're going to dynamically allocate this memory. Now, when I say dynamically allocate, what I mean is that it's allocated at runtime. For instance, if we have this array, that's allocated at compile time, okay? But this is going to be allocated at runtime when the actual program runs. So there's a function called malloc, which stands for memory allocate. So if we say data equals malloc, and then we have to give it a size. And you have to bear in mind, let's say we want 10 million. That's all well and good, except that's 10 million bytes or 10 million chars, which are the same size. The problem is an integer is actually, we're compiling in 32 bits, so it's 4 bytes. If we're compiling in 64 bits, it's 8 bytes and so forth. So what we have to do is multiply this times the size of int. Okay, and this will take care of the size of the type, and this will take care of how many we want. And at that point, we declare integer variable counter. We can say for I equals 0, I is less than 10, I plus plus. We say data sub I equals I times 2. I'm just making this up, that has really no meaning. So now notice that when we talked about arrays in class, we talked about that arrays are implicitly a pointer, right? If we have this, this is implicitly a pointer. Okay. Remember how in scanf and things such as that we didn't even need to put the ampersand in front of it just because the compiler treated it like a pointer? But now this is explicitly a pointer. We've actually explicitly declared it and allocated it, and it's now a pointer. So we go through here, we do this again. So here are the assignments. We've assigned that what really, it's still an array. Even though we dynamically allocated it, you can still treat it like an array. So if we say printf %d data sub I, and if we run this, I'll have to break it because this will run forever, or it'll actually run for quite a while. Let's see, build and run. Okay, actually, it's a different window. Okay, so it's going to run a long time since that's 10 million. I'll just hit Control C and it'll quit, and so forth. Now, on the same vein, you really actually could, see this is data sub I, but there's something called pointer math. You could actually say data, which that's wherever the data is pointing to. And then after that you can say data plus plus, which goes to the next element in the array. And since it's an integer array, it'll go to the next one. So this actually is going to give you the same as this. Okay, so let's go ahead and run that. Just verify that that actually works. This always runs. I've got two monitors, and I've got to kind of manage that. Okay. This is actually called pointer math. And if it was a char, it would add 1 going to the next char. If it's a short, it would actually add 2 going to the next short. Since this is an integer and an integer is 4, it'll actually, the address will actually go to add 4 and go to the next integer. Now, I'm going to go back and put this where I was. There's another thing you really need to realize is that once we allocate memory, it's our responsibility to free it. This is where you're taking memory from the operating system, or really from your process space. And once you do that, you really need to give it back, because if you don't give it back, there's definitely a potential that you could run out of memory because you use it, and if you don't give it back, you've got it locked up, and so you want to always try to give the memory back whenever possible. Well, you really just need to have a rule of giving the memory back. Okay, so another important point I want to make is that I'm doing integer here, but this could be float. And if it was float, I would just change this, and I just say F here, and it will probably run okay. Now that's a float, okay. Let me go ahead and make it a double. See, what I'm trying to demonstrate is it's the same principle whether we're using ints, doubles, or floats. Okay. Let's go and run this guy. Okay, so we can do a short here. Actually, this value would really be greater than the value of a short. So what we'd have to do is say like I divided by 4. Otherwise, you see, even if that's, let's say I divided by 100, because otherwise will be short is a value from 0 to 65,535, and otherwise that'll be too great of a value. So we want to make sure that we're not exceeding the value of a short. Okay. Anyway, so now let's go ahead and talk about linked lists. So a linked list is a sequence of nodes, such as we have here. Each node has a value, or in that might be a data structure, it might be a numeric value. Normally for what we're going to be referring to, we're going to be referring to linked lists as structures. So there's a value, and A, B, C, and D are going to be sort of the whole contents of a data structure. Okay. And then there's a link to the next node, right? So each link points to the next node. Now notice D does not have a link to a next node. Its link to a next node is actually null. Okay, the last node contains what's known as a null link, which lets you know you're at the end of the list. Okay, the list may or may not have a header. Now, in your homework assignment, you should have a header. So you're going to have a header that's that global variable that's a data structure. Okay, so in your homework, you're going to have something that is a header. Okay. So a node successor is the next node in the sequence, right? Whatever it's pointing to. The last node has no successor. It's really a null successor, but you know that when you hit null as the successor, you're at the end of the list. Node's predecessor is the previous node in the sequence. Now, we're not going to be talking about this right now, but there is something called a doubly linked list where you can actually like link up a level. We're only linking our linked lists are only going to be one way, but there is a possibility that you can have two-way linked lists. The first node has no predecessor, as the last node has no successor. A list length is the number of elements in it. A list can be empty with no elements. Okay. So in C and C++ we have pointers, which we've talked about. In Java we have references. And the only reason I'm sort of mentioning Java right now is because eventually you'll get to object-oriented programming and CS2 where you use Java. And so it's kind of the same idea there, just a slightly different syntax and paradigm. Okay, the difference is that in C and C++, they allow you to modify pointers in arbitrary ways. In fact, we've already talked in this video about pointer math and so forth. References in Java, you can't do that too. In other words, in Java, a reference is more of a black box, so you really can't do anything to it. The Java runtime actually, and this is true in C# and Haskell and so forth, other languages where you don't have direct memory access, but basically what it's doing is managing the memory for you. Okay, so malloc is what we use to allocate any kind of object or structure or array or whatever. Malloc returns a pointer to whatever that object is that you allocated. And here's an example. Struct person P. That actually should. Yeah, I just did a quick edit on these slides. It really should be asterisk P since this is a pointer. Sorry about that. Anyway, asterisk P equals malloc. And this the code malloc size of person creates an object that gives you exactly enough space for that person structure. Okay, so the first thing we're going to do is create a structure with contact info, which we've done in class a number of times. Let's see if we can get this done quickly. Yeah. Now, this should look pretty familiar to you. But what we're going to add here now is a pointer to the next data structure in the list, in the linked list. Okay, so this is what we've been seeing now for several weeks. The only difference is we have a pointer to the next one down the list. Okay, now as your assignment says, we're going to have a global struct contact info CI. Okay, it's global. And what we need to do is figure out a way to add to this. Okay, so add a, let's say add contact info. Okay, and notice I'm not going to pass anything in here as a parameter because we're going to be working off this global data structure. So the first thing we have to do is we have to walk to the end of the list. Okay. So what we're going to do is say while first, let's say struct contact info tmp equals CI. Okay. So now that's going to be pointing to this global CI. But now we're going to do what's called walking the list. So we're going to say while TMP next does not equal null. So if it doesn't equal null, there is a next in the list. If it does equal null, then there isn't a next in the list. Okay? In other words, if I find that TMP next is not null, then there is a successor, as we've talked about before. Otherwise, there is no successor, and this is the last in the list. Now notice we're going to start off with no successor because this will end up being null. Okay. Now remember, a globally allocated anything structure is going to default to all zeros. Okay. But what we want to do is we want to walk to the next. So we want to say TMP equals TMP next. And what this is going to do, this is going to allow us to walk the list as long as there is a successor. Okay? And this will walk, here we have the global structure, we're pointing to the global structure. Now we're going to keep doing this while there is a successor. Okay? If there is a successor, we're going to say point TMT to that successor. Finally, when we get here, we know that there's no successor. Okay, if there's no successor, then what we're going to do is we're going to say TMP next equals, and now this is going to be a new one. In the previously we've used malloc to allocate memory. It's actually a bit easier if you use a very similar call called calloc. Because what calloc does is it zeroes out all the memory. Okay, so I'm going to say size of struct contact info. That's almost identical to malloc, and I'm going to say 1. Okay, so I can allocate as many of those as I want. Okay. Difference between malloc and calloc: malloc just allocates memory. Calloc allocates the memory and goes ahead and zeroes it all out. And if it's zeroed all out, then basically what that means is if it's all zeroed out, then that means that next, the successor is null. Okay, but we remember how there was no successor. We finally stopped when there was no successor. Now that we've allocated memory, there will be a successor here. However, the allocated structure won't have a successor. Okay. So let's go ahead and create a function called ask for user info. And I'm going to do this. I'm going to try to do some speed programming. Enter first name. Okay, so here's our ask for user info function. And now we're going to call that 3 times from main. Let's go ahead and build and run that. Just make sure everything's okay. First name Rick. Occur. 123 Main Street. Okay, so let's go ahead and run this, see what happens. Okay, now it's going through all this the second time. I'm just going to go ahead. Now there's one thing we probably are going to have to fix, and that's that the address is normally going to be have blank spaces, and that'll actually throw us off. So let's use a getS here, and that'll just be better. Now once we've added all of these, what we can do is go ahead and display all contact info in list. Okay. I know my function names tend to be fairly long. Okay, we'll get used to it. All right, so here we go. We still are going to have to do the same thing. We're still going to have to walk the list. Okay, we're going to walk the list in the exact same way that we did before. Okay. Now, one thing we have to realize is that the very first data structure has no data in it. Okay, so we just have to remember that there's no data in the data structure. And I'm actually in that first data structure. It's actually functioning sort of like the header. Okay, so really what we need to do is, if we do tmp.next, it's not going to actually display anything in that first record. We'll fix it. Let's say display single record struct. Having trouble typing. Contact info tmp. Okay, so this is neat. We're just going to use printf for this. %s tmp first tmp last def %s let me put a comma there. %s and this is going to be for tmp address tmp city tmp state tmp zip. Finally, we'll output the phone, printf %s tmp. We actually are going to need \ns here, otherwise this will look really bad. Okay, so that should be good. So now we're going to display single record tmp, okay, and then we're going to use the same trick we used up here to walk to the next, to the successor, and this will stop us. Okay, so let's go ahead and run this guy. Now, this is actually, we're going to have to make a fairly significant change to this. Oops, a typo there. We're going to have to make a fairly significant change to this to make it work correctly, but it's okay. Taking the easy way out on typing this stuff in. Okay, so notice this first record here doesn't have any information. The next record correctly has R, the next record correctly has Q, and the last record should have had E's, the letter E, but it doesn't. Now the problem is, as I said, the very first record doesn't have any information in it. Okay, so the first time you come through this, it's going to show you a blank record. Another problem is we don't really want to stop when the successor is null. We just want to stop when this is null. Okay, so the best way to do this actually is to make a change to this. So we're going to wait until tmp does not equal null. And that way we'll get to that very last record. So we'll get to the last record, but we also want to skip the first record. And we're going to say if tmp next does not equal, actually it's fine. We're just going to say tmp equals tmp next. And that way, Since the first record is blank, we're going to go to the successor right away. Okay, so now that we've made that change, let's go ahead and build this and make sure everything's okay. And let's go ahead and run it and make sure that okay, so there it displays all the data structures correctly. So what you're going to have to make sure that you do is when you display it, make sure you skip over that first data structure, okay? And that's really all you have to do to ask for input. Now, one thing we can do here, let's go ahead and change this just a bit. And let's say char answer, let's have a do while. And this way they can add as much as they want. While stricmp answer quit does not equal 0. We'll say add contact information, and then we'll say printf type quit to end, anything else to keep going. Scanf %s answer. Okay, so get rid of these. And actually, one more thing I'm going to do. We're sort of having an issue. It's hard to, the operating system doesn't seem to like to mix scanf and getS. So I'm going to change all of these to getS. And that'll give us a better result, actually. You may have noticed it skipping over one of the fields. And so this will prevent that from happening. And the last thing we'll do is we'll change this down here to a getS. Okay, it just doesn't, so the runtime just doesn't like to mix scanf with getS. So let's go ahead and in code blocks should easily tell you what to do. Rick, 123 main, Orlando, Florida, 33333, 123. Okay, so now let's say no. Let's do one more. Sam Spade 444 333. And then we'll say quit, and that's going to display all the records that we added in there. Okay, so this is good. So far, we're doing really well. Now, you could actually save all of this to disk, and I don't think the assignment calls for this. Well, let's go ahead and put something up here where we save all records to disk. And so file fp equals f open c info.txt, and I'm gonna W will create it for our writing text, and we'll go ahead and error trap this. Just to make sure, I need to make sure I get you in the habit of doing that. And just to also make sure, let's go ahead and close it here. Okay, now we're going to go ahead and do this. We're going to go ahead and walk the linked list. And remember that the first record is empty, so we're going to say tmp equals tmp next. So we're kind of So we're going to kind of skip over the first one, okay? So while tmp does not equal null, Now, in order to walk, we're going to print this stuff to disk. But for right now, at the very end here, let's say TMP equals TMP next, and that will go to the successor, right? So we'll say F, print F, and I'm just going to do this in a really easy way. Oops, B. There's no escape code for B. TMP first. I'm just going to do a bunch of these. Let's see, last address, city, state, zip, phone. Okay. Address, city, state, zip, phone. Okay. And what that's doing is walking through the linked list and saving each record. Now, you could do a similar process to read in the records too, but I'm not going to do that in this presentation.